Hey guys, so jumping in here today to talk a little bit about orbits of planetary bodies. Just one reminder here to pay attention to, especially to the words that are in bold and underlined or highlighted, because those are definitely going to be some of the topics that you may see again on the quiz and the quick check. So, how do planets move in the solar system? So Kepler, we're kind of returning back to talk about him a little bit. In addition to Tycho Brahe, who had collected quite a bit of observations and data. So Kepler kind of based all of his theories and or laws that he proposed on a lot of this data. And so he formulated what we know now about how planets move in our solar system based on Brahe's observations and his own. And the planet that he was studying was not moving in a perfectly circular pattern. It was actually what we would call elliptical. So if you take a circle, a perfect circle, and then squish it and almost make it look like egg shaped, that's elliptical. So elliptical is basically kind of oval. So Kepler's contribution, he has three laws actually, but the funny thing is about the first and second, even though they're labeled as that, they weren't discovered in that order. So his formulation of his second law is actually what led him to then be able to form his first law, which is what we just talked about, the elliptical orbits. And then based on the fact that they have elliptical orbits, the second law, which remember he did discover that one first, states that the planets, such as Earth, for example, orbit around the sun on an imaginary line from the center of the planet to the center of the sun, and it sweeps equal areas, and so over an equal amount of time. So equal areas, equal time is how that works. Let me move this. I can't. So here's a picture of this right here. So these are the areas, these blue type. Some of them are, well, they're all triangles ish because this leg of it is not actually round, so it's curved. So these areas, which are figured having to use some geometry based on the fact that it is partially circular, not all straight lines, but in any case, these areas stay the same no matter where the planet is located in relation to the sun. So that's what the second law basically encompasses. And that's what led him to say, oh, wait a minute, the pathway is not a circle, it's actually an ellipse. So that's how the second law actually led to the first law. And so while we're looking at this picture, we can also then talk about gravitational force. So as you are thinking about this, this is just an example. The sun and the earth orbiting the sun. You can also think of it in terms of our moon orbiting the earth. So when the planet is approaching the planetary body that it is orbiting, you have two forces both aimed in the same direction. So the inertia of the planet is forward because it's moving in that pathway and it's going to continue to move in that pathway. That's one of Newton's laws of inertia, unless it's acted on by an outside force. And in this case, the outside force is the gravitational pull from this body, which happens to be the sun in this example. Both these arrows pointing in the same direction relatively, they're being added. So the power is increased. So the gravitational force and plus inertia speeds up this orbiting body. Okay. So as it's getting pulled toward the sun, it's speeding up. And as it goes around the backside, is at its closest, and then basically it gets slingshot around. As it starts to move away, now you'll notice one arrow is still pointed back to the sun because the sun is still pulling it in, but it's losing its power to do that because now inertia is focusing away. And so because it's in the other direction, it is decreasing the amount of its speed. So the more the distance increases away from the sun, the speed decreases because now you have forces opposed to each other. So they're being subtracted. The path it's moving on is called the orbit, and the gravitational force is that force between these two objects. So every Anything that has mass is going to have a gravitational force to another, or attraction to another object. And so this that's description. So when objects are in motion, this there's different kinds of motion. So as two objects draw close together, the force between them increases. So as you think about them getting closer and closer together, it's like, can't be two magnets because they would then so opposite poles. But as they get closer, then you can't even hold them apart anymore, and they're attracted. So it's similar to that. Not quite the same force, but you get the idea. So then, as you pull them apart, that attraction becomes a little bit less. It's similar to that. So as the objects grow closer together, the force increases. Okay, so increased force equals increased speed. So when you put those two in the same direction, you get increased speed. Retrograde motion and apparent retrograde are very similar because it appears to be counter to the usual direction. And what you have to think of is in this picture, it is showing you that your vantage point is changing because we are on an orbiting body, and then there's a orbiting body in front of us, and then what we're seeing in the sky looks at a totally different pathway based because we're also moving, if that makes sense. So it almost looks like it's going backward, but it's because of our angle that we're viewing it from. That's why retrograde looks unusual and almost seems to be backward motion. So how do we get to an ellipse? There's three pathways that objects can actually take. You have spiral, where an object eventually spirals, and we pretty much it gets caught in that gravitational pull. I'm sure you've seen it on videos or movies, and it eventually spirals down into that orbiting the object that it's called the central body. That's what's causing the attraction. So that object can spiral down in. So when we talk about meteorites, sometimes they come in a spiral orbit that eventually lands them and crashing. If it's a meteorite, it has crashed. So then you have the hyperbola, which is the one that swings around and then away in like a U-shaped one-way trip. So it comes around one time and then slingshots out into space, and it doesn't continue in the orbit. Sometimes we attach that to objects that are not created or formed in our galaxy or our universe because our orbits are all wet. They're all elliptical. So when we have objects coming in, like sometimes comets will do this, we know that if they're on a hyperbola shaped orbit, didn't form in all likelihood in our solar system. So then you have the ellipse. An example here is as the Earth moves closer to the sun, as we showed in the picture before, that gravitational force increases because both of those arrows are pointing the same direction. The Earth's inertia and the gravitational pull are pulling us toward the sun. So then the reverse happens as we come around the other side and move away. Now we have the Earth's inertia pointed in a different direction as the sun pulling us back toward the sun, and they basically cancel each other so that the speed decreases. Notice that it's highlighted. So orbital speed, you have acceleration, and that is simply defined as a change in an object's motion. We think about accelerating as going faster, but acceleration means change. Simply change. It can change by speeding up, it can change by slowing down, or going a completely different direction. And so when you have those three options, it can be any one of those. The formula is acceleration is equal to force divided by mass. So mass is important. It's definitely part of this calculation. So the speed of an object in orbit, therefore, depends on its distance from the central body and the mass of the central body. So when we talk about the sun being massive compared to the Earth, and it has this very large gravitational pull on it based on its mass, but it also depends on the distance that we are from the sun, which is why our speed changes as we're approaching and then as we're going away. This is a two-body problem when you have two bodies that you're talking about, remembering that they attract each other, but if one mass is larger, then the attraction is bigger. If they move further apart, then the force gets smaller. So these are all things to take into consideration when we're having to calculate the two-body problems. So detecting wobbles, This is based on that central body. So, if we're talking about, for an example, it's best explained by the Earth and the Moon. So, the Earth has a much larger mass than our Moon, and so if you think about the Moon orbiting the Earth and that distance, remember that central area stays the same. You tend to think of it as, okay, from the Earth's core to the Moon's core, and that just stays the same. If you could put a string and two pieces and wrap it around, but it doesn't work that way. It doesn't always mean it's the actual center mass of the orbiting of the central body. So instead, for example, in the Earth Moon system, the actual center of this actual relationship is more located in the Earth's mantle, not the core. So the mantle being almost to the outside area of the Earth and not in its center core. That's where the center is figured. And remember, this is like some geometry here. So you just need to know that the center of the circular orbit is not the exact center of the central body. And the central body is the one with the larger mass, or that's being orbited. Okay, so in this case, the Earth being orbited by the Moon, it's not in the core, it's in the mantle. So not the exact center. So in summary, for example, this the planet Neptune says Uranus was observed deviating from its expected orbit, and scientists discovered Neptune's gravitational force was pulling on Uranus outside of its orbital path. Now, Uranus, the orbital path was what was kind of, it was expected to be elliptical, but all of a sudden, Uranus was acting outside of its actual expected orbit, and they hadn't even discovered Neptune at the time, but because of Uranus's behavior, they were able to determine that there was actually another planet out there. And every time that Uranus got close enough to its gravitational pull, it kind of made it wobble outside of its expected orbital path. And so it pulled it away. It decreased and it pulled it out of its orbit, made it wobble a little bit. So as the moon moves away from the Earth, the speed of the moon decreases, and so that was that relationship. If it's moving toward its orbiting central body, then it's going to increase. If it's moving away, then it's going to decrease. So you just need to remember that relationship toward the central body. The speed is going to increase. Away, it's going to decrease, because you have two forces fighting each other. And Tycho Brahe collected the original data and observations, upon which Kepler added his, and then did some formulations and some of that geometry, and figured out and supported his suggestions, his laws outlining how planets move in our solar system. And as a planet approaches the sun, the attractive force between them increases, as does the approaching planet's speed. So if we're talking about the Earth, for example, as the forces of attraction go up because the gravitational pull plus inertia, then the Earth's speed is going to increase as well. So, orbital motion of planets can tell us so much about what's going on in our solar system. I hope you were able to gather some facts there and some understanding. And if you didn't take notes, go back and watch this again, jot some notes down, print these slides, keep them open for your quick check. You remember, you can use your notes on all quick checks and quizzes. Thank you so much.